Suppose if you have taken methane and if you have taken chlorine in excess, what you will get? Yeah, Nabil, Samaira, tell me. If you are doing this reaction is known as photohalogenation, and if you have started the photohalogenation of methane, okay, and you took excess of chlorine, so then what you will get?
Carbon tetrachloride.
Yeah, carbon tetrachloride. Because if you are taking chlorine in excess, so first time photohalogenation, you will get CH3Cl, second time you will get this, third time you will get chloroform and carbon tetrachloride. What is the common name for carbon tetrachloride? Tell me. Yeah, Nabil. Samara. What is the common name for carbon tetrachloride? Yeah, it is pyrene. It is also used as a fire extinguisher. Okay, clear? So, and suppose if you take cyclopentane, you will get uh, chlorocyclopentane, and suppose if you take cyclohexane and you do the bromination, that is very simple. How can you maximize the yield of CH3Cl? Can anyone tell me? Yeah. How can you maximize the yield of CH3Cl? Yeah, Nabil, Samara, quickly tell me.
Sir, could you repeat, sir? How can you maximize
The yield of CH3Cl. Means what can you do so that you can get CH3Cl as the main product?
Reduce CH4.
Yeah, actually you need to take methane in excess. Suppose if you take methane in excess, what will happen? The chlorine will react only with methane. The chlorine will not react with CH3Cl further, because everywhere you have methane. How this CH2 dichloromethane, how chloroform and how CCl4 are formed? Okay, they are formed because you took chlorine in excess. So whatever you get, that reacts with chlorine again. Okay, and that's why you get the reaction keep on happening. Okay, and it doesn't stop. It stop finally at CCl4. Okay, but if you take methane in excess, okay, if you take alkane in excess, then monochloro derivative is the major product. Okay, this is known as monochloro derivative because there is only one chlorine attached to it. This is known as dichloro derivative. This is known as trichloro derivative, and this is known as tetrachloro derivative. So if you want to have the maximum yield of monochloro derivative, you need to take alkane in excess, and in this case, the alkane is methane. If you take the methane in excess, the chlorine will have a chances of reacting only with methane because everywhere you have taken methane in more amount. So you will get CH3C. Okay. Suppose if you have cyclopentane, cyclopentane can react with Cl2, right? And chlorine, you will get this. Okay, bromine, you can get this. Okay. And mechanism. Yeah, this is the mechanism. Mechanism has three parts. Okay, and what are these three steps known as? It is written over here. Yeah, Nabil, you can tell me. Samara, you can tell me what are these three parts of the mechanism? They are very important. Yeah, quickly tell me. It is initiation, propagation, termination. Okay, initiation means the reaction starts, you give some energy, you give some light, you give some heat, the Cl2 break. Okay, the Cl2 break and Cl2 break into Cl radical. Okay, and it is homolysis because both are Cl. So if you give the energy, it doesn't happen that it breaks as Cl plus and Cl minus, it will break as Cl radical, Cl radical. As you can see over here, what these Cl radical will do, they will attack and break the H. Okay. because everywhere they have the alkanes around them. So they will react with the alkane, they will collide with the alkane because Cl radical is already having one electron, it will collide with hydrogen, okay, and you get HCl and methyl radical. Okay, methyl radical again, it is a reactive intermediate, so it will again react, collide with Cl2 and it will break Cl, and that's how your product is formed, right? So this is the way in which the reaction happens. Okay, but these are propagation steps. Okay, so can you tell me which step is the rate determining step?
The slowest step, the bond breaking
Yes.
step.
Yeah, slowest step. But which step is the rate determining step out of the initiation and propagation step?
Initiation step.
Which one?
Initiation.
No, initiation is not the rate determining step. We can prove that. Okay, it is not the rate determining step. The rate determining step is actually the breaking of H radical by Cl radical. This is the rate determining. This is the slowest step. Okay. Suppose, and how can we prove? What is the method to prove? The first method is, instead of methane, you can take CD4. Okay, what is CD4? A methane with deuterium isotope, which is heavy hydrogen. Okay, and it is stronger. It forms a stronger bond. So you will observe that the rate will be slowed down because that CD bond is stronger. Another thing is, listen very carefully. Suppose if you want to prove that the first step is not RDS, it may appear that the first step is slowest. Okay, the whatever you are thinking is as per the normal way. Okay, normally we feel that okay, the first step is the rate determining step. But let me tell you one very important point. Suppose if the first step is the rate controlling step, okay, so then the rate will depend upon the bond dissociation energies of halogen. Okay, what are the bond dissociation energies of halogen? Can you tell me? Samira, Nabil, do you know this? Bond energies. Okay, why the F2 is having less bond energies? Can you tell me? What could be the reason? Samira, Nabil, can you tell me?
Yes, sir.
Why the F2 is having low bond energy? Actually, you want F2 is smallest, so it bond should be strongest. But it is not the strongest bond. It is actually close to its energy. It is a weak bond. Okay,
Because
why?
it is highly electronegative.
No, actually what happens is, suppose if the bond is smaller, so it is going to be stronger. But what happens if it is smaller? In the case of fluorine, there are 6 lone pair. If it is smaller, these 6 lone pair are going to come very close to one another. They are going to repel. And that repulsion will make the F2 bond very weak. Is it clear?
Yes, sir.
Okay. So F2 is not the strongest. It comes just next to I2. Okay. Cl2 is the strongest bond. So as we were thinking that the first step is RDS, okay, if the first step is RDS, what should be the rate of the halogenation? This is a famous question. If the rate, I will say it in simple words. If you assume, you can also write it. If you assume that this step is the rate controlling step, initiation step is the rate controlling step, then what will be the rate of, by looking at the bond energies of halogens, what will be the rate of reactions if you assume that the first step is the rate controlling step? Is the iodination is going to be fastest, or is it the chlorination which is going to be fastest? These are the bond energies as per the bond energies. And if the first step, initiation step, is the rate controlling step, which one do you expect to be the fastest one? Yeah, Nabil, this is also a good question. Samaira, tell me, which one do you think will be the fastest? Yeah.
Iodine.
Chlorine?
Yeah. Is it the iodine or chlorine?
Chlorine?
Chlorine? No. Chlorine bond energy is strongest. It is the strongest. Okay. So iodine should be, iodine is the weakest bond. Okay, bond energy, if it is less, the bond is going to break very easily. And if the bond is going to break easily, the reaction is going to take place very easily. Okay. And if the rate is dependent on the first step, which includes the breaking of halogens, and the halogen bond energies I have already given to you. So chlorine is having the maximum bond energy. That's why it is at the first position. Okay. So chlorine is actually having the maximum bond energy. So chlorine is most difficult to break. So iodine should be the most easiest one to break. And if iodine is the most easiest one to break, the rate of iodination should be the maximum. But actually, the rate of halogenation is of photohalogenation. It is not the iodine which is the weakest, which is going to react most easily. It is fastest for F2, then Cl2, then Br2, and then iodination is going to be the slowest. This is fastest. And this is slowest. So this trend of the rate of photohalogenation is not matching with the bond energies. Okay. So the bond energies will not decide the rate of the reaction. So first step is not the rate determining step. This step is the rate determining step. Do remember this, okay? And do remember this point also. And there are chain termination steps also. Chain termination step actually lead to the stopping of reaction. The reaction will stop. Okay, why it will stop? Because there are radicals and those radicals will combine one another. They will join and they will again form a Cl2 or ethane or methyl chloride. So if the radicals dies, okay, if the radical is not there, there is no reaction. Okay, that's why it is known as chain termination step. Okay, means the reaction is going to stop, right? Clear? So I hope this is clear to everyone. Samaira, Nabil,
Yes,
any doubt? Any doubt in this? Actually, what I have discussed is asked in the form of questions. Okay, and the most common questions are, so which step is endothermic? Can you tell me? Another question. Which step is endothermic? Yeah. Is it the termination step or initiation step?
Initiation.
Which step is?
Endothermic. Which step is always endothermic? Endothermic means which require heat.
First step, initiation.
Yeah, initiation is always endothermic, right? Termination is going to be always ectothermic because there is bond formation. Okay. So let's move to the next thing. Suppose if someone asks you, there is a alkene given to you, and if I do the chlorination, suppose so in methane, actually we have seen, we have connected 1 chlorine, 2 chlorine, 3 chlorine, 4 chlorine, okay? So that we got monochloro derivative, dichloro derivative, trichloro derivative, tetrachloro derivative. But if someone asks you how many monochloro derivatives you can get, means this is a very common question asked in all examination. How many monochloro derivatives are possible if you carry out the photohalogenation of a given alkane? The answer, to write the answer, you need to think that at how many places, how many different places are there where you can put Cl, and how many different structural isomers you can get upon putting 1 chlorine. Monochloro derivative means, okay, this is monochloro derivative, 1 chlorine. If you put 1 chlorine, how many structural isomers you can get? Okay, total number of monochloro derivative structural isomers which are possible from the given alkanes. Okay, so tell me how many you can get from A.
5.
5. Why 5, Nabil?
There are 1, 2, 3, 4. There are
Because
5 carbons.
yeah,
So
yeah, good. There are 5
at each
carbons.
carbon.
Yeah, so each carbon. But you need to look one more thing. One more thing is, are those all carbon different or are they same? Okay. Suppose if I put chlorine here, I will get 1 fluoropentane. There are 5 carbons, so it is pentane. Or if I put chlorine at this position, we will call, okay, we will get 2 fluoropentane, right? Because this is the second position. If you put Cl this, you will call it 3 chloropentane. But if you put Cl at this position, Nabil, what you will call it?
2 chloropentane.
Yeah, it is same as that of this one. Okay. So initially, we need to think about the number of carbon atoms, but we also need to check that are the all carbon atom different, or some of the carbon atom, the molecule is symmetrical and some of the carbon atoms are same from this side and that side. If there is a symmetry, then you will not get different compounds. Okay, so this will be one Chloropentane, this will be 2-chloropentane. This will also be known as 2-chloropentane. This will be 1-chloropentane. But this one is different. This is 3-chloropentane. Okay. So total, how many monochloro derivative you will get? Structural isomer. I'm not talking about the stereoisomer. You will get 3 monochloro derivatives. Clear?
Yes, sir.
3 monochloro derivatives you will get. What about B? How many monochloro derivatives you are going to get if you attach 1 chlorine? What are the possible structures? You need to look, you don't need to look at the each and every carbon. You need to look at the symmetry. If the
Sir,
molecule
three?
is, yeah, you are very close to the answer. Yeah, I think 3 only. You are correct. Let me check. So this point and this point are same. And same is the way this point and this point, because this is symmetrical. Okay. Because on, if you look at both the sides, this side and that side are same. Okay. So this carbon and this carbon are same because they are on the either side of the middle line. This one and this one are same. Okay. And all these 4 groups are also same because they are on the equal distance. Okay. Yeah. So totally you will have 3. Good. So 3 is the right answer. 3 structural isomers you are going to have. Is it clear? So we will come to C. C is the question which is asked in almost every examination. Though it was first asked in JEE Advanced, but later this question became so important that it was asked in JEE Mains. It was asked in many examinations. Okay. Clear? So we will talk about C. First, let me discuss what is D. How many monochloro derivative you will get from D?
3.
How many?
3.
From D?
Yes.
From D you will get only
Sir, 4. 4.
4.
Yeah, sir. 4.
Samira and Nabil Khan, would you like to try? You will get only
1.
1. Yeah, correct. Why 1?
Because no other compound is present. So you will
Yeah.
need only pieces of that chlorine.
Yeah. Actually, this is a symmetrical compound. Okay. This is a regular hexagon. Is it clear? So regular hexagon, all the carbon atom are same. It is not that this carbon atom or this one or that's one or that one or this one or this one, though you can number them. But if you turn it like this, all the carbon are interchangeable, they are same. Is it clear? So if they are same, suppose if you put Cl here, this will be 1-chlorocyclohexane. Okay. Or simply chlorocycle. If you put Cl here, you will not say I will count from here and I will call it as 2. No, this is again 1-chloro. Is it clear? If you put Cl on it, in this case, that is again 1-chloro. Okay. All are same. But this is the most symmetrical compound from all of the compound which we have seen. Okay. So only 1 monochloro derivative you will get. Is it clear?
Yes, sir.
Yes, sir.
So this is very important. Now let's come to C. C is the very famous question. And I told you it was asked in JEE Mains, Advanced, NEET. Okay, all examination, very common. Yeah. So tell me how. So this is actually the name of this compound is. Okay. 2 methyl pentane. Okay, such kind of question are asked everywhere. Yeah. So how many monochloro derivative you are going to get? Tell me. From C.
Sir, is it 4?
Oh, okay. This is what. Okay. We need to cover the whole molecule. Okay. First of all, we can't stop in the middle, as we did in the above two cases, A and B. There we stopped in the middle and not proceeded beyond middle, okay, line, because it was same. So it was just a repetition if we cross that middle line. There
Sir,
is
five.
no, yeah, let me check. Okay. And there is nothing called symmetry, okay, in this in middle line kind of thing. So you can have your chlorine this at this point, you can have it at this point, you can have it at this point, you can have it at this point, right? All will be different, okay. And but these two methyl are same. Why they are same? Because they both are CH3 and they are both connected. Not every methyl is same. Be careful. Suppose if two methyl groups are connected to the same carbon, okay, we can swap them like this. Both of them are same. They're not going to be different. Okay, so we need to look at them, okay, in a same way. Okay, so 4 at these positions, and the fifth one will be both of these. Anyone you can choose to put Cl. So total 5. I hope everybody is agreeing with this, right? So yeah.
Can you explain?
So just check the answer. Clear?
Sir, and E, question E, how is it 5, sir?
How is it 5? Okay, very good. Let me explain it. One is this carbon. Another is this. This one and this one are same. Why? Because if you move from this, if you start from methyl, if you go on the right hand side, if you go on the left hand side, it is same. Do you agree with this, Nabil?
Yes, sir.
And similarly, if it is this one and this one, they are also same. Because you are moving this way, this one, that way, they are same. And this one. You can write their name also. I will suppose if you have any confusion, okay, I can write the name. This is CH3 NCl. Okay, 1, 2, 3. Okay, 1 chloro 3 methyl cyclohexane. Okay, if you put Cl on this side, that is also same. 1, 2, 3. 1 chloro 3 methyl cyclohexane. Is it clear? So it is same from both the ways. Clear?
Yes, sir.
So that's why 5. And what about E and F are very important. Okay. Yeah. Raj, welcome to the class. Yeah. And how many monochloro derivative you will get from F? So this methyl and this methyl are same. It is not that the one is green colored and another is red colored. Okay, both are same. You can do it like this. And this one is this one are these two carbon are also same. These two are same. These two are same. Okay. So that's how, and this is the middle line. Navi, is it clear? So if you have the middle line, the upper portion and the lower portion are both same, right? So how many different? 1, 2, 3, 4, 4. Total there are 8 points, but out of those, the 4 points in the above section and the bottom section are same. Is it clear?
Yes, sir.
Yes, sir.
So this is the very important question. So how many monochloro derivatives are formed? Structural isomer. I have not yet covered the stereoisomer. That is very, very important. Okay, I will tell you. So now let's move to some questions. Okay. Yeah. So try to do this question quickly.
Sir, A.
Yeah. The reaction condition leading to the best yields of ethyl chloride. In the dark, the reaction will not happen, Miraj. Yeah, so A is the right answer. You need to take UV light. Okay, so the reaction can happen. Okay, but if you take ethane in excess, the chlorine which is there in the reaction that will can collide only with ethane. The probability of collision will be only with the ethane because you have taken ethane in excess, large amount. The chlorine can react only with ethane. So if chlorine can react only with ethane, you will get only ethyl chloride as a major product. But if you take option C, then what will be the answer? If you take option C, yeah, tell me quickly.
Carbon tetrachloride.
Yeah, not carbon tetrachloride. You need to say some other word because this is not the methane I have taken. This is ethane. So if you take chlorine in excess, all the hydrogen will be replaced by chlorine, right? And you will get somewhat similar to carbon tetrachloride, but here you have 2 carbon and 6 hydrogen will be replaced by 6 chlorine. So it is hexachloroethane. Is it clear? 111,222 hexachloroethane. That will be the IUPAC name of this compound. So C will be, because you have taken chlorine in excess, so all hydrogen will be removed and you will have chlorine. But if you want only one chlorine, if you need to put only one chlorine, so you must somehow ensure that the chlorine should react only with the ethane one time, and that insurance that you can get that can be insured by taking ethane in excess amount. Is it clear? So A is the right answer. Okay, good. So yeah, this will be the answer. So let's move to the next question. This is the same question which I talked about you, which has been asked in many examinations. Okay. Yeah, now it has become a very famous question. So it is very common. Yeah. So tell me quickly. Total number of structural isomer possible when one hydrogen is replaced by chlorine atom in the given compound. This is isopentane or 2-methyl butane. Yeah.
So 4.
Uh, 1, 2, 3, and this one are same. So I will take, though there are 5 carbon atom, but both methyl, I will take only one of them. So 4. Yes, correct. So now we need to talk about the rate of halogenation. And as I told you that the fluorination is very reactive. Can you tell me why fluorination is very reactive and you can't control it? What is the reason for it? that fluorine actually is very, very reactive. Yeah,
High bond energy.
bond energy was very weak actually. The bond energy is not as per this trend. The bond energies are Cl2 is the strongest bond, then Br2, then F2, then I2. So one thing is bond energy is very weak. So if the bond is weak, it can break easily, it can react. But again, I told you that the bond breaking of halogen is not the rate determining step. It is something else. Okay. Another thing, so we need to look at something else. Okay. So another thing is that this fluorine, when it forms a bond with carbon, a bond which we get is carbon fluorine bond, that also is very strong. Okay. Because fluorine being the smallest. So it releases a lot of heat. That's why it is highly exerted. And you know, or you will study in kinetics that with every 10-degree rise of temperature, the rate of reaction get doubled. Okay. The rate of reaction get doubled. Okay. So the heat liberated will make the reaction faster and faster. So more heat will be liberated. And that's why it becomes uncontrollable. The heat liberated is so high that it breaks the carbon-carbon bond also. Is it clear? Right?
Yes, sir.
Yes, sir.
Okay. So what is the remedy for it? Then how will you, so never do fluorination directly. That is the thing, Samara. Suppose if someone asks you, can you do fluorination? Can you attach fluorine by photohalogenation? No, don't do it directly. Otherwise, you can't control that reaction. So what is the method? You will take Schwartz reaction. So what you do? You can take chlorides. What reagent do you take in Schwartz? Have you studied?
Yes, sir.
Yes, Samira. I have not heard your voice. Yeah. It is AGF, right? COF2. Yeah. Okay. So this is displacement reaction. So directly fluorine you can't attach. So do it indirectly. Take chloride or bromide and react with AGF. F will come and Cl will go on. Clear? And so fluorination is never carried out directly. Suppose it is so exothermic that it breaks even the carbon-carbon bonds. So if you take ethane, propane, they will all break in and form an alkane with one carbon. Okay. The next thing is what about iodination? What about iodination? Yeah. What you expected from iodination? Iodination you expected to be the fastest. Clear? Because iodine is the weakest, it is the largest of all. So you expected that it is going to react very quickly. It is going to break very quickly. That's true. It requires the least energy to break into I radical. But I radicals form very quickly, but being a very large radical, because you know that the fluorine is from the second period, chlorine is from the third period, bromine is from the fourth period, iodine is from the fifth period. So iodine radical form very quickly. Okay, but what happens is it forms, but it stays as it is. It doesn't react further. Why it doesn't react further? Because of its bigger size, that unpaired electron is there, no? So that is an 5p orbital, which is very large. So that electron is very much dispersed on a large area. It is not able to form bond with carbon. That's the reason that you can't do iodination directly. In spite of having a weak bond, still you can't attach iodine. It is very unreactive towards halogenation. So if you take iodine, if you take alkane, most of it will remain as it is. Okay, very less product will form. Okay. Similarly, in fluorination, the reaction was very fast. Fluorination start even in dark because it itself is releasing a lot of heat, so you don't have to give any energy. Okay, but fluorine, it is so reactive that you can't control the which product you want. It break carbon-carbon bond also, so you never do fluorination directly. Instead, you use substitution reaction, which is known as Schwarz reaction, to put fluorine. Similarly, iodination is also not done directly because it will not give you product. The reaction will not be complete. So you use, there are two methods to attach iodine. So one is Finkelstein reaction. Okay. And another one is you can suppose if you want to do photoiodination. Any idea? Any one of you? Nabil Khan, Nabil Ahmed, Mehraj, Samira. How to do iodination? Yeah, tell me quickly. Yeah, who is going to tell me what is the way? This reaction is completely in the backward side. Whereas means you are not getting the products. So what you need to do to get more products? This is an equilibrium reaction, reversible. So you might have studied in class 11. Suppose if an equilibrium reaction is there and if it is not getting completed, what you need to do? Lee-Chatterjee principle. Who is going to explain it to me? Yeah.
Increase the reactants.
Increase the reactant or yeah. Or remove the products. Okay. So what I will do? Suppose if you increase the reactant, the reaction will be pressurized to move in the forward direction, or remove the product. Removal of product will again do the same thing. Okay. So what I will do both together. Okay, I will take an oxidizing agent. Like HNO3, HGO, HiO3. So what these oxidizing agents will do, they will oxidize the HI. So your HI will get consumed and it will get oxidized to I2. So if the reaction is not getting completed on its own, what you do, you take oxidizing agent that remove IHI. So this is a question. Okay, do remember this. Okay. Clear, Miraj, Samira, Nabil?
Yes, sir.
Okay. So how will you carry out iodination? This is the photoiodination in the presence of oxidizing agent. What is the role of oxidizing agent? Actually, they consume the liberated HI and they oxidize it to I2, and that's how the equilibrium is pushed in the forward direction. The second way is by displacing. You can attach fluorine and chlorine easily. So attach them. Once they get attached, displace them by iodine. So that displacement reaction is known as Finkelstein reaction. Okay. So that is known as Finkelstein reaction. So you can see over here. So what you do, you take some chloride and bromide, which is already can be prepared easily by photohalogenation, because there is nothing, no problem which we observed in chlorination and bromination. The kind of problem which we observed for chlorination and iodination. Chlorination was too reactive and iodination was too unreactive. But that kind of problem is not there. You can get to chloride and bromide, and once the chloride and bromide are there, you can react it with any I. This I minus is going to come and join to Rx and XY, because carbon can make only 4 bonds. So if I is attaching, the X should come out. Okay, that's all. And there is also a role. So you take NAI in acetone. So there is also a role of acetone. Actually, this is more soluble. You might have studied Pajan's rule in class 11, chemical bonding, which explains that ionic compound acquire covalent character due to polarization by the cation. So NAI is somewhat covalent. It is soluble in covalent compound like acetone. NaCl and NaBr, Cl is more electronegative, so they are more ionic. And if it is more ionic, it is going to be insoluble in acetone, which is an organic compound. You know who can get soluble and who cannot get soluble, depends upon, can be expressed in simple words like dissolves like. Okay. So, actually the equilibrium is pushed in the forward direction, because whatever the NaCl, NaBr are forming, they are getting precipitated. Is it clear? So this is Schwarz reaction. Okay. Nabil, Miraj, Samaira. And this is Finkelstein. So these two are asked, their name is asked. Okay, what are their reagents? AgF is the most common. Hg2F2, cobalt, and SbF3 can also be used. Finkelstein reaction, they both are displacement reaction in which the chloride and bromide are displaced. Right? Samaira, clear?
Yes,
Any
sir.
doubts? Any doubts? I hope it is clear. Miraj? Okay. Now the next thing is chlorination and bromination both can happen, because they do not have any problems which we faced while doing the fluorination and iodination, which was not happening directly. So we don't have those problems while we do chlorination and iodination. Okay. So now the thing is, what to use? Should we use chlorination or bromination? Both can happen. So let me get into the detail of both of them. We rejected fluorination. We are not going to do on our own in the presence of light. If someone asks us to attach fluorine, we will do it by using Schwarz reaction. If someone asks us to attach iodine, we will not do it directly. We will take the help of Finkelstein reaction, in which we take NaI acetone. But chlorination and bromination both we can do directly. And what are the advantages and disadvantages? So chlorination is more reactive. Chlorine is more reactive. You can see chlorine is more reactive and bromine is less reactive. Okay. So if something is more reactive means it is less selective. Means it can't make out where it is going to get attached. It can attach everywhere. It's just like, suppose if you are hungry and if you reach your home, then whatever is there at the home in the fridge, okay, and if the food is not cooked, you will eat it. Okay, you will be less selective if you are more hungry. So chlorine is actually more reactive, it is less selective, it can get attached to any carbon. But bromine is very important because in most of our reactions, we are going to use bromine. Bromine is less reactive because it is a bit larger in size, so it is more selective. What do you mean by more selectivity? Means the selectivity means bromine can differentiate between the type of hydrogen atom, and it will attach itself only to those type of hydrogen atom which can break very easily. Okay, so how hydrogen can break easily? Who will decide? Nabil, Samaira, Nabil Khan, can you tell me which hydrogen can break more easily? How can you tell it? Yeah, Nabil, would you like to add something? So this is the compound, and there are three types of hydrogen in it. This is primary hydrogen. This is secondary hydrogen. This is tertiary. This is primary again. You need to look at the carbon atom, and this is tertiary. Clear? So now you tell me, bromination is very selective. So where bromine is going to attach itself? Where bromine will attach itself? In this compound, you need to tell me, Samara.
On the tertiary carbon.
Tertiary. Why tertiary? Tell me. Yeah, Nabil. Any idea why tertiary carbon?
Because carbon is already attached to three other carbons. So the bond between hydrogen and carbon will be comparatively weaker and easier to break.
Yeah, weaker and easier to break. So yeah, tertiary hydrogen is the most easiest to break, but who is responsible for it? Okay, Br radical is formed and it breaks the hydrogen away. And you get a tertiary radical. This kind of. So which is having carbon on three sides. Okay, this is secondary radical, this is primary radical, and this is methyl radical. Okay. And even more easily than the tertiary, allylic radical can break very easily. Okay, and the benzylic radical also can break very easily. What is the reason? The reason is not the hydrogen. The reason is the radical, how stable that radical is. Suppose if the radical is getting stabilized, then okay, it will let the hydrogen get departed very easily. The hydrogen will break very easily. But if the radical formed is highly unstable, then it will be difficult for that X radical to break that hydrogen, means the energy of that CH bond is going to be high. So I can write bond energy of the CH bond. You can also write it, note it down. Okay, is inversely proportional to the stability of the carbon radical which is formed after the removal of H radical. Here, if the radical formed is stable, then the bond is going to be weaker. It is going to break very easily. But if the radical formed is unstable, then the bond will be very strong. It is not going to break. So now the whole things come on the stability of carbon radical. Now, students, tell me, what makes C radical stable? What are the factors which can make carbon radical very stable? Yeah, suppose this is a benzylic radical, this is allylic radical. Why they are leading the stability order? Tell me. Yeah, Samara, Nabil, tell me quickly. I need to hear only one word that will explain the complete thing. Which is, and that word will tell me why these radicals are very stable and leading the stability order. And the explanation is also there in front of you. Okay, what is that word? Yeah, tell me quickly. What is the stabilization factor?
Resonance.
Resonance. Yeah, right. So this is, suppose this is allylic radical. Allylic carbon is the carbon which is adjacent to the double bond. Okay, and this hydrogen can break away very easily. Why it can break away? It's not the color of the hydrogen. Okay, it is not colored in fact. Okay, it is the stability of the radical which is formed when the hydrogen is taken away by the X radical. So look at the, look, I'm trying to draw the YT picture. So this is the unpaired electron radical which is formed, and adjacent to the unpaired electron there is a double bond. Okay, this is the double bond. So this p orbital of the radical, because double bond is just a neighbor of this, it just overlaps slightly with the double bond. So this electron, unpaired electron, which was formed on CH2, can mix up, can move into the double bond and can get mixed up with the electron densities of the double bond. How it will affect? Okay, so I have shown you the resonance structures. Okay, because I can't show you the animated movie here, right? Animated movie can tell you that, okay, this electron is getting mixed up. So instead of showing the animated movie, what I will try to do, I will draw the one by one structure to make you realize that, oh, the electron can come on this side, that side, it can go this places. Means it is getting mixed up with the electron densities of the double bond. So these are the resonance structures of the uh, allylic free radical. Okay, this is the radical. So this can form bond with a double bond. Double bond has two electron and this is having one. So this one electron can overlap with this. Okay, there is a double bond formation on this side and this is double bond. The radical will come on the other side. Okay, and that's how the radical will get mixed up with the double bond and it can get stabilized. Okay, so that is the reason why allylic radical can form or the hydrogen can form very easily. Is it clear? Same is the case with benzylic hydrogen also. Benzylic hydrogen is not the hydrogen of the benzene, but it is the hydrogen of the carbon atom which is connected just outside the benzene. Okay, this is the benzylic carbon atom, and its hydrogen can be cleaved very easily. It has having the very less energy. Why that hydrogen can be broken very easily? It is because of the radical which is formed here. The radical is very stable, and this radical benzylic radical which is formed on the CH2 is adjacent to the benzene, which is having 3 consecutive pi bonds. Okay, and they are doing the resonance, cyclic resonance. Their electron density is mixed up, and this radical electron density can also get mixed up. Okay, that's how it will become stabilized. And this is the one by one resonance structures which will show how this is doing the resonance. Okay, and this is the hybrid. Hybrid is the overall structure. It is just like the animated thing with the electron is shown. Okay, it has been distributed at all the this position due to mixing up. Okay, so the final structure is a resonance hybrid, which is the average of all the structures. You might have studied all of this in class 11. Okay, we are doing the revision. Okay, so you don't have any problem. Okay, and suppose allylic and benzylic radical are resonance stabilized. You said it very correctly. Now tell me why the tertiary radical and secondary radical are stabilized. What are the factors which can stabilize tertiary and secondary radical? Nabil and Samara, Nabil Ahmed, Nabil Khan. Tell me, what are the factors which can stabilize tertiary radical? Yeah, quickly tell me. Yeah, they can't do resonance because there is no double bond. Samara, can a tertiary carbon radical can do resonance? No, there is no double bond. So then what? The thing which can stabilize this tertiary radical is hyperconjugation. Okay, what is hyperconjugation? Tell me quickly. Who is going to explain me the hyperconjugation? Yeah, Nabil, tell
Sir, could
me.
you repeat, sir? Hydro?
Hyperconjugation is the factors. For example, in the benzylic and allylic radical, it was resonance, which was responsible for the stability of the radical. It was mixing up of radical electron with adjacent double bond. I'm asking you what are the factors which stabilize this tertiary radical, which make tertiary radical more stable than secondary, and secondary more stable than primary, which in turn is more stable. What is the which factor is responsible, and that is hyperconjugation, right? I will write over here. Is it clear? So what is hyperconjugation? Tell me quickly. Yeah. So suppose this is the tertiary radical, right? And these are the hydrogens. Okay. So this unpaired electron get mixed up with the electrons of the adjacent CH bond. How it get mixed up? It is also known as sigma p conjugation. Okay, this is the electron, this is a CH bond. Okay, and this CH bond has two electrons. This unpaired electron and this electron can form bond among themselves. Okay, that's how they can get delocalized, and you will have this kind of structure. Now the radical character has come on hydrogen. Similarly, it can come here, it can come here, it can come on these 6 hydrogens also. So these are alpha hydrogens, right? These are alpha hydrogens. Okay, alpha hydrogens, and they are responsible for hyperconjugation, right? Okay, how many alpha hydrogens? Alpha hydrogen are the hydrogen which are actually adjacent to radical. Okay, alpha carbon. There are 3 alpha carbon. So wherever you are having radical, there are the 3 adjacent carbon, and the hydrogen connected to them can turn by turn overlap. By giving the one of their electron can turn by turn overlap with that unpaired electron, which is on the tertiary carbon atom, and that's how your uh, unpaired electron will get paired up. It will get stabilized. This phenomenon is known as hyperconjugation. And how many hydrogens are there responsible for the hyperconjugation? There are 9 alpha hydrogen, 3 on each. Okay, turn by turn they can overlap with this unpaired electron, and that's how it will get stabilized. Okay, hyperconjugation. So suppose if you have tertiary carbon atom, okay, and if you have secondary carbon atom, secondary carbon atom can also do hyperconjugation. So these are the 4 radical. This is tertiary, this is secondary, this is primary, this is 1 degree, and this is not 1 degree, this is just methyl radical. Okay, 1 degree. So how easily up to what extent they are stabilized by hyperconjugation can be found out very easily by counting the number of alpha hydrogens on alpha carbon. Those are the carbon which are adjacent to the carbon bearing radical. Okay, so here you have 9 alpha hydrogens, here you have 6 alpha hydrogens. Okay, they can turn by turn, 6 alpha hydrogen can turn by turn, let's say, give their electron density, and that can make this radical stabilized. Okay, so tertiary radicals are also very stable, but they are not as stable as resonance, as radicals which are doing the resonance. It is because the resonance, the electron which are getting delocalized are the pi electrons, which can get delocalized very easily. But in the case of these alkyl radicals, the hyperconjugation is responsible for the stabilization, but it's because it is the delocalization of sigma bond, CH bond, so it is not as effective as, though it is effective, but are not as effective as resonance. Okay, in stabilizing the radicals. So resonance stabilized radicals were placed before in terms of stability, they were leading the stability order, followed by the radicals which were just normal radicals, secondary radical, tertiary radical, secondary radical, primary radical, which are just stabilized by hyperconjugation. Is it clear? So that's how we decide the order. So I hope hyperconjugation is clear.
Yes, sir.
So Samira, be very careful. It is just like suppose if we go to school and if we have forgot to take our tiffin. So suppose if we have 9 friends, what they will do? They can share the tiffin, okay, with you. So you will not realize that you have not taken your lunch box, okay, because those your 9 friends can give your lunch box, okay, turn by turn, and okay. So same way hyperconjugation also stabilize that. Okay. So a lot of questions come on hyperconjugation. So be very careful. But resonance stabilized radical are more stable. So bromine is having less energy. So bromine is very selective. And just now we have seen the stability and the order of radicals and the bond energies of the CH bonds. There was some CH bond like allylic and benzylic CH bonds were cleaved more very easily. And there was some tertiary CH bond was also cleaved very easily as compared to the secondary hydrogen connected to secondary carbon. Okay, and hydrogen connected to secondary carbon was cleaved more quickly or more easily than the primary hydrogen. It is because of the hyperconjugation. Okay, and there is a difference in stabilities, and that difference in stabilities will lead to the bond energies of the CH bond. Okay, and but the bromine is having a less energy. Okay, bromine is like an old person. Okay, let's say. So it is going to break only that hydrogen which can be cleaved very quickly or by giving least amount of energy. Okay, so bromination is having less, bromine radical is having less energy, just like an old person. So it is very selective. Okay, and if it is very selective, it will, on the basis of the energy order, it will break only selected hydrogen which are most susceptible to get cleaved. Okay, so suppose if I do the bromination of this butane, which is a major product which I will get, or if I do the bromination of this 2,2,5 trimethylhexane, what is a major product which I am going to get? Nabil. Then if I do the bromination of ethyl benzene, where I am going to connect the bromine? Nabil Khan, tell me quickly. Yeah. Just quickly tell me everyone. Yeah. So you need to check. This is primary carbon, this is secondary carbon, this is secondary, this is primary. So Br can get cleave most easily the secondary carbon. Okay. Clear? So what is the major product? Samira, can you hear my voice?
Yes, sir.
Have you understood why the bromination, if there are 1 degree carbon and if there is 2 degree carbon both present simultaneously, the bromination is going to take place on the secondary carbon? Nabil Khan, can you hear me? So this is a major product. Because the radical can, this hydrogen can break more easily because it is secondary hydrogen and it has alpha hydrogens on both the sides. Okay. And so this is the hydrogen which can, so radical can form here, so bromine is going to get attached. Okay. And bromination actually it is, if you do the chlorination, and chlorine is very reactive, it is itself having, it is like a young man. It is having a lot of energy. So it doesn't matter whether For chlorine, it doesn't matter whether the hydrogen can be broken more easily or less easily. Okay, chlorine itself is having a lot of energy and it will break any hydrogen on its own. So that's why the chlorine can get attached itself to any carbon. There is no selectivity, right? But bromine is like old person, so it will just selectively choose the positions where it can get where it can break the hydrogen most easily. That is secondary out of 1 degree and 2 degree. So that's why this is the major product. And that's why we are saying that bromination is very selective. And what about this one? You can see here there are all types of carbon in this molecule: primary, secondary, tertiary. Okay, but the major product, if suppose if someone asks you how many mono bromo derivatives, that's a different question. In that question, you are going to put, or you are going to check all the possibilities where you can put bromine. Some possibilities will be more, some will be less, but you need to write all the products. Okay, but if someone asks you what is the major product, then you are going to give only one answer. The answer which is formed in major amount, okay, in main quantity, that is a major product. So bromination, as we have seen, is very selective. So it is, this compound is having a lot of carbon atom, and out of all those carbon atoms, the tertiary carbon atom, the tertiary hydrogen is the most reactive. So bromine can get attached at this point. This is the major product. Okay. What about this one? Just now we have seen that there is a benzylic carbon, the carbon atom which is just directly outside the benzene ring. This is the benzylic, not this one. And this, its hydrogen can be broken very easily. It is having the least energy. Okay, right? Because it is resonance stabilized. So if it is resonance stabilized, it can come out very easily. And if it can come out easily, it can form that. It is because it's radically stable. Okay, and if it's radically stable, it can come out easily, and a BR can get attached at this. Out of all the positions, the PR attached itself on the benzylic position only. Is it clear?
Yes, sir.
Okay, so this is a very, very important thing. Selectivity of bromination. You need to check the compound. Yeah. So you just give this answer quickly. What is the IUPAC name of the major product formed when you treat 2-methylbutane with bromine in the presence of sunlight? Nabil, Ahmad, Nabil Khan, quickly tell me, both of you. Yeah. Yes. Which one will be the major product? Yeah, you need to check each and every carbon, whether it is primary, secondary, or tertiary. Okay, this is primary carbon. This is secondary carbon. This is primary carbon. This is primary carbon. And this is tertiary carbon. There you can see. This is tertiary hydrogen. There is one hydrogen and it can break very easily, most easily. Okay. So bromine can break this hydrogen very easily because the tertiary radical is very stable. So where you are going to put bromine at this point? Okay. It is 2-bromo, 2-methyl butane. Right, this is going to be the answer. I hope it is clear to everyone.
Yes, sir.
Okay, so do check the answer, very, very important. This is the most common topic. It has been asked everywhere. Now, this is the last question. What will be the answer to this? You need to tell me. Yeah.
1 bromobutane and 2 bromobutane,
Yeah.
in which 2 bromobutane will be a major product.
Yeah, major product. But how many different products? Yeah, you are
Two, sir.
correct. Including stereoisomers that are written in red. This is one, and there are two possibilities here. Two stereoisomers. If you don't count the stereoisomer, you will call it as one. If you consider it stereoisomer, you will consider it as two. So you need to read the question very carefully. Suppose if they ask you how many, so in the last questions which we did today, in the beginning at A, B, C, D, E, F, those were the questions in which we just discussed the structural isomer. That's it. So you need to select where the chlorine is going to get attached, bromine is going to get attached. Okay, and this question is a bit different. You need to tell the products, but you need to also consider them their mirror images. Okay, stereoisomers. You need to tell me that whether do they have different mirror image isomer. Okay, by keeping that in mind, you need to answer this question. If they have a mirror image, means they can have two possible options, right? And they can form a product. Is it clear? Okay. So total answer will be 3. Samira, you know this one. We will discuss it on the next turn in detail, and we will take some more examples, okay, of this kind, where you need to think about the stereoisomers and when the compound can have stereoisomers, okay, how to look at it, and how to check them, that you can study, okay, from the book, whichever you are having referring. We can discuss some more questions on it. Is it clear? So any doubt in today's lecture, any topic? Hyperconjugation is very, very important for all examination, but not for boards, much for boards, CBSE. But if you are preparing for NEET and JEE, then it is very, very important to know why a tertiary radical is more stable than secondary radical, who is responsible, that is hyperconjugation, and what are alpha hydrogens, how they interact with the radical